All right, so we're on example 13 here, and we've already done it one way. We're gonna start doing it. Today's lesson was doing it the other way. All right, so this was a definite integral, if you recall, from 0 to 1, and by pattern recognition, it's very, very quick and easy. Remember, you don't need the plus c. As long as you have the evaluation bar, we got 15/8. But you have the option, if you are a fan of u substitution, and again, in some cases, it's actually going to be required. If it's a definite integral, you kind of have a nice option here. What would you call u, by the way? X squared plus 1. So if u equals x squared plus 1, let's go ahead and start our integral. Instead of x squared plus 1 cubed, we've changed it now to u cubed. And we still have a few things to replace. Of course, we have the x dx to replace still. So if I take the derivative of both sides in differential form, du would equal 2x dx. Now notice that I don't have the 2 in my integral, so I need to solve that for x dx. And to do that, I'll multiply both sides by a half. So I have a half du equals x dx. So that 1/2 ended up being what we had as our correction. So what that means now is I can replace the entire x dx with a 1/2, which I can pull out front, and a du, which is always the right bookend. Now for an indefinite integral, that's as much as you need to change. But we have a definite integral. So these values here, these intervals of integration, are what types of values? They're x values, right? We read that as the integral from x equals 0 to x equals 1. So if it's a definite integral, you have two options. You can evaluate it as an indefinite integral, do it with terms of u, then put it back in terms of x like we're used to doing, and then evaluate it still from 0 to 1, or just change your intervals of integration from x values to u values, and then don't look back. So let's do that. When x is 0, what is u? We'll plug it in there. U is 0 plus 1, which is 1. So we'll change the lower bound. And then the upper bound, when x is 1, u is 1 squared plus 1, which is 2. So now, since we've redefined the definite integral, and this is kind of interesting, as a completely different function on a completely different interval, we can evaluate the new definite integral, and we're going to get the same value, which is kind of interesting, because it's two separate regions on two separate intervals, but they have the same exact net accumulation. So let's just compute it. What is 1/2 goes along for the ride? What's the antiderivative of u cubed? Yep, 1/4 u to the 4th. Good. And we don't need a plus c. We could evaluate it from 1 to 2. Now here's where you can get kind of in trouble. If you didn't change those values and you evaluate it from 0 to 1 without changing it back to x, that would be like answer choice A on the test, right? Because that's a common mistake. But if you have changed them from x values to u values, just proceed. Now the 1/2 times the 4th, that's a 1/8. I would recommend leaving your constant multiples out front. So you get 2 to the 4th minus 1 to the 4th. And again, on a free response, are you done? Yeah. On a multiple choice, you think that's going to be an answer choice? Maybe. No. We'll keep going. 2 to the 4th is 17 minus 1 is 16. Minus 1 more is 15. There you go. Don't ask me how I do math. 15/8. Y'all recognize that number? Yeah. That's the same number we got when we did it yesterday. Now, of course, which way is a little faster? Pattern recognition. But it only works if you recognize the pattern. Yeah. U substitution is more of a formal process that it does work. And it does help you because it simplifies your radicand dramatically. So if it's an indefinite integral, remember, and you do use substitution, like right up here, you cannot leave it in the end as a function of u. Like this line here, you can't just walk away because it's an indefinite integral. You have to replace u back with what it was. But if it's a definite integral and you use u substitution, as long as you change the intervals of integration, you don't have to put it back in terms of x. Okay? Pretty neat. All right, let's kind of transition towards what we warmed up with, which I'll do with Mr. Peck. Review the following antiderivatives. So these should be quick and easy. Now notice the dx is in the numerator. That kind of looks funny, doesn't it? Sometimes it's put there just to be more economical, instead of having the right book in there, remember dx is an individual quantity, so you can treat it like a factor. So you could put it in the numerator, but this kind of looks more recognizable. So don't freak out if you see it in the top there. That is the derivative. That integrand is the derivative of what? Arc sine. Good. Of x plus c. So the square root of 1 minus x squared. That's number minus function under a radical. This one here, I'm not going to rewrite it, but that's the one we saw in the warm-up. That is the derivative 1 over 1 plus x squared is arc tangent of x. And, of course, plus c. If you want, you can write it as inverse tangent of x, right? That works. Which means you can write it as tangent of x to the negative first of x as well. Is that right? Which means you can write it as cotangent of x plus c as well, right? No. This doesn't work. That doesn't work. Remember that when you put the negative 1 notation like that, that is reserved exclusively for inverse notation. But if you wrote it as tangent squared of x, you could write that as tangent of x squared, right? So because of the inherent confusion with the inverse notation, that's the whole reason we have what to begin with? The alternate notation. Okay, so just be aware of that. Just a gentle reminder. Gentle. And this one. Arc secant. Yeah, that one's pretty noticeable. It has a radical. It's function minus number, and then it's got the x on the outside. Now, if you're going backwards, if you recall, this becomes arc secant of not just plain old x, but absolute value of x. Yeah, plus c. Okay, so if you actually run into those guys, you know what the answer is. But what we're going to be doing now is what if you run into something that's kind of like that, but it's not perfectly in that form? Well, you're going to be able to either manipulate it by doing a whole lot of algebra so that it fits this form, or you could just memorize the results of those patterns. And this is what Mr. Peck did with y'all. So if you haven't memorized these yet, please do so. I'll go through them with you, and then I'll show you why they work, okay? So these are going to be your 3 forms that you're going to memorize. If you ever have the integral of, and you have in the denominator the square root of number minus function, and you've already gone through and the pattern recognition doesn't work. In other words, the derivative of the inside function inside the radical is not the other factor in the problem, or only off by a constant multiple, okay? It's kind of like our last resort. If you have number minus function, then that's going to be an arc sine. You have to identify the number, which is a, and the function, which is u. So you're going to be staring at a squared and u squared. If the derivative of u, which we're calling du, is the other factor, or again, only off by a constant, then it goes straight to this form. It's arc sine of u over a plus c. There is no 1 over a built into the rule. It's the only one that doesn't. All right. Like the warm-up, if you have something over number plus function and pattern recognition u sub doesn't work, then identified a and u. If the derivative of u is the other factor or only off by a constant, it goes to this form. 1 over a, arc tangent of u over a, of course, plus c. And then the last one here, if it's function minus number with whatever you're calling u as another factor outside, then if you can identify u and a and you're only off by a constant in the derivative of u, then it's 1 over a arc secant of the absolute value of u over a. Memorize those, okay? And if you don't want to memorize them, I'm going to convince you that it's worth memorizing them as we work through some of these examples, okay? So on example 15, we're going to compare and contrast, and then we're going to write a 3-page paper. No, wrong. No, we're not. Never mind. Let's look at these. A and B. They look very similar, right? They look very similar. But they are very different. Okay? Which one do you want to do first? You don't have to do them in alphabetical order. B. Oh, nice. Jaime said B. Let's do B first. Why not? What would you do? The first thing on your mental flow chart is you realize that you have a function of x divided by a function of x, right? And if you wanted to like just put everything on a level playing field, you might bring that to the top and say it's to the negative 1/2. So now that you have a product. Which factor is more complicated, x or the other one? Yeah. The other one. So it probably has the inside function, 4 minus x squared. That possibly could be u. Let's see. What's its derivative? Negative 2x. Do we get the critical x part? Yep. We're only off by a negative 2. So it's going to work. So we have a correction of negative 1/2 The x now gets packaged back up, and we're on to step 2 already. We have the rule of integration. What is our inside function actually inside of? It's inside of blob to the negative 1/2. That's like u to the negative 1/2. So the antiderivative by the power rule would be blob to the negative 1/2 plus 1, which is, bless you, positive 1/2. And then, of course, instead of dividing by 1/2, we will instead multiply by 2. And then put plus c, and we're done. Because by the power rule, remember we add and divide. So when I add 1 to negative 1/2, I get positive 1/2, and then I divide by 1/2. But instead of dividing by 1/2, we multiply by the reciprocal. Yeah. I know when I walked in, Mr. Peck had he always divided by the new number and then maybe cleaned it up in the next step. But the whole purpose of pattern recognition is to do it quickly and efficiently. So if you ever have a fractional exponent from the power rule, just put the reciprocal in the front. Yeah. Okay, then cleaning that up, we end up with the negative square root of 4 minus x squared plus c. And we're done. And we're smiling the whole time. Okay. So that's with the x on the top and the dx off to the side. Let's retreat now to a. Notice we don't have an x on the top anymore. If you want to pull that dx off to the side, we're left with just a 1. Now, certainly the presence or absence of that x in the numerator really should have little to no bearing on the outcome of the problem, right? I mean, it's just a little x, right? So is that going to be another power rule integration? No, but that would be an answer choice because the derivative of that is negative 2x. Now we're off by an x, and you can't make a correction of an x. You can't make a correction of a variable. So it's not going to be a power rule, which means we're kind of now at the end of our rope, really. It was a very short rope. I guess we can kind of like, can we take the square root of each of these terms? The square root of 4, can we call it 2 minus x in the bottom? That's horrible math. Don't do that. We can't split anything up. Golly. What do we use maybe as a last resort? Or if we just recognize the pattern immediately? Inverse trig. So it has a radical, so it can't be arctangent, right? Can't be arctangent. Now, which one is it? Is it arcsine or arcsecant? It's arcsine. And it's because it's number minus function. It has nothing to do necessarily with the fact that there's nothing out front of the radical, because you'll see that that doesn't really matter. Subtraction is not commutative. So arcsecant is function, a variable, minus a number, and arcsine is a number minus a function. So this might be arcsine. We still have to check it. If this is arcsine, then 4 is a squared, and a is 2, and x squared is u squared, and u is x. Now, you have to check. Don't skip this step. This is like u substitution. You're calling x the blob. What's the derivative of x? 1. Is that the other factor in the problem? Yeah. Are we off by anything? No. We're ready to go. It is an arcsine. There's no rider other than a 1. There's no correction. Does arcsine have a 1 over a in front? It does not. So we go straight to arcsine or inverse sine of u over a, which is x over 2 plus c, or 1/2 x. Either way. And there's your answer. Now let's check. Right? Let's check. How do we check to make sure that's right? Take the derivative. Let's take the derivative. What's the derivative of arcsine of blob? 1 over the square root of 1 minus blob squared times the chain rule, the derivative of the blob, which is 1/2. Yeah. And if you compare that to your original integrand, same. They're the same. Exactly the same. What the? There. They don't look anything alike, do they? Uh-oh. What do we do then? Well, I guess we have some algebra to do. We could do that, right? Let's simplify. Oops. How about 1 over the square root of 1 minus x half squared is x squared fourths times 1 over 2. Well, the 2's already there. You know what? I don't like 2 in its current form. I'm going to send him on a covert mission here. Okay? I'm going to put him in disguise. Good disguise, too. Now, ready? You ready to infiltrate the enemy? Now that he's got his radical, he can go inside, right? right? It's a reconnaissance mission, really. So now that they're both square roots, this 4 could be a factor in the denominator inside the radical, right? Which means you can distribute it. And if you distribute the 4 to each of those terms, what do you get? 4 times 1 is 4 minus 4 times x squared fourths, x squared. And there you go. Good job. Good job, 2. You get the Mathematical Medal of Honor. Okay, so it does work. So it works. Now, if you didn't want to memorize the form, guess what you would have to do algebraically? When you see something like this, 1 minus x squared, if you didn't memorize the form, you would actually have to do exactly what we did here, but in reverse. You would have to put it into 1 minus x halves squared form. And you would have to say, oh, x halves is now my inside function. Its derivative is a half. This 1/2 goes along for the ride. I'm off by a 2, and that's a lot of algebra. Okay, you wouldn't want to do that. So just memorize the forms. Let me show you what that would look like. Okay, because it can make for some interesting commentary, I guess. You would have to say, okay, my arc sine form has a 1 there. That's a 4. So how can I make a 4 of 1 besides just subtracting 3? I'm going to have to divide through by 4. I'm going to have to factor out a 4. Let's do that. If I factor out a 4, I get 1 minus, how do you factor a 4 out of x squared? X squared fourths. Okay, good. Hey, now I have the square root of 4, which is the same as 2. So I have 1 minus, and then x squared fourths, that's the same as x halves squared. And now I can pull the 1/2 out front, and I get 1 minus the square root of 1 minus blob squared. And now, by pattern recognition, this would be the blob, and its derivative is 1/2. If this 1/2 goes along for the ride, and you're off by 1/2, you would have a correction of 2, and then it becomes arc sine of the blob plus c, and of course those divide out, and you get the same answer. But that's a lot of algebra to do, and that's an easy one, actually, to work on with the algebra. It doesn't always work out that nicely. So, memorize the forms, and everything goes lickety-split fast, right? Okay, very good. C and D, once again, very similar but kind of different. Which one do you want to do first, C or D or C? You already chose. Which one did you say? C? C? C. C. Okay, bueno. I'm going to pull that dx off to the side. ¿Verdad? Sí. Sí. All right, my inside function's at the bottom of the first power. It's a natural log rule, right? Nope, we got to check first. What's the derivative of that? That's what you would normally call the inside function. Again, this is you going through your mental flow chart. The derivative of that is 18x. Do we have an x factor in the top? No. We don't. We're off by an x. Can we make a correction of an x? Nope. So it's not going to be a natural log rule. So, golly, can we split up the terms? Can we say it's 1 over 2 plus 1 over 9x squared? Can we do that and be right? No, that doesn't work. So I guess it's going to be maybe inverse trig, maybe. And there's only one of them that doesn't have a radical, and it's arc tangent. So it's not for sure an arc tangent, but it's maybe an arc tangent for sure. If that's a squared, then a would be what? Square root of 2. They don't have to be perfect squares. And if u squared is 9x squared, then u is 3x again. Now, we check. What's the derivative of what we're calling u? What's the derivative of 3x? 3. Crap. We have a 1 up there. We're off by a 3. Is that really a problem? Nah, it's not a problem. So we've got it. So we know that there's no rider other than a 1, but we do have a correction of a third. Now, we're on arc tangent. Does arc tangent have, as part of the rule, built in a 1 over a? It does. So we have a 1 over the square root of 2. What's the only one that doesn't again? Which one? Arc sine. Good. And now we go to arc tangent of u over a, which is 3x all over the square root of 2. I should call that u, plus c. And you're done. Simplify the numerator, or the coefficient if you want, 1 over 3 square root of 2. But you're done. Typical answer choices for these inverse trigs would be like a natural log for people who have no idea what they're doing, but they think they do. And then a couple of arctangents, one that has a 1 over a in front and one that doesn't have a 1 over a in front. And that would be the only difference. So you'd have to know. Okay, sweet. Now, so D. This one looks similar, but again, It's different because now it has an x in the top. So as you go through your mental flow chart, it's not immediately an arctangent because it could be just a use sub pattern recognition for something else. If this is your inside function, its derivative is 18x. The other factor is x. We're only off by an 18. So now we've got it. So we have a correction of 1/18. The x gets packaged back up, and now we have 1 over blob to the first, which of course is the natural log. That one's the natural log. Very good. Now, if you see an answer choice that doesn't have absolute values in this case, it's for a good reason. They're only there to make sure that the argument is positive. 2 plus 9x squared, like my wrong answer in the warm-up, is always positive. So you can get rid of them in this case without any consequence. But that's not just an absolute thing that you could do every time. Little Pekingese going for a poop, if you want to take a look. Pekingese poop. All right. It is. It is. Yeah. All right. Compare and contrast. It's good to see things that are similar but different, right? Different methods. And really all it is the presence or lack of the presence of a single x, a single factor. All right. The arc-secant integration pattern can be a bit high maintenance, like diva ladybugs. All right. Evaluate the following. 9 over 5x. Oh, it's happening. Oh, it's cute. When he's done, the little feet go. Oh, cute. Okay. Anyway, that's from pretty green grass out there. Is there anything we can pull out front, constant multiple-wise? 9/5. Good. I love having windows. I love having windows. Okay. There you go. The inside function you could call, going through your mental flow chart, x squared minus 16, right? It's inside the more interesting factor. What's the derivative of x squared minus 16? 2x. Are we only off by a 2? Very good. If to be only off by a 2, that x that's in the denominator would have to be in the numerator. Because really it's not x, it's 1 over x, right? So the derivative of x squared is not 1 over x. So that is not going to work. That is not going to work. So you got to be careful. You can't just have an x anywhere. It has to be in the right spot. It's notation, notation, location, notation. Very good. So, Kyle Lee, what can we do? Maybe inverse trig, huh? It's got a radical, so it's not arctangent. It's function minus number, so it can't be arcsine. I guess it has to be arcsecant, if it's going to be anything at all. All right, let's try it out. If x squared is u squared, then u is what? X, good. And if 16 is a squared, a is 4. Now, there's two things that have to be fit the bill for this to be an arcsecant. The first thing is, as usual, the derivative of what you're calling u has to be the other factor in the numerator or only off by a constant. What's the derivative of x with respect to x? 1. We're not off by anything. But we also need whatever it is you're calling u to be just conveniently located right outside the radical. And is it? Yeah. Okay, perfect. Nice. So two things need to happen. So both of them work. So 9/5 goes along for the ride. Is there any correction? Do I remember? Was there a correction? Nope. Do we have a u over a for this one? I'm sorry, a 1 over a in front. My bad. Still thinking about that stupid dog. We do have a 1 over a in front. We do have a 1 over a in front. Now we go to arcsecant of the absolute value of u over a plus c. There you go. There you go. So it's 9/20ths arcsecant of a fourth of absolute value of x. Now what if it's a multiple choice question and you see an answer that's not the absolute value of x over 4, but it's the absolute value of a fourth of x? Is that okay? Can we just bring the 4 inside the absolute value? The 4 is always positive anyway, so there's no harm in bringing them in, right? So that these are actually equivalent. Now, if that were a negative 4 down there, you wouldn't just bring the negative 4 inside and make it positive, okay? So yeah, it could be that. All right, so that one wasn't real high maintenance. We just had 2 things to check for instead of 1. Letter B. Real quickly, mental flow chart. 4x squared minus 9 could be your inside function, could be a power rule. What's the derivative of 4x squared minus 9? 8x. Are we only off by an 8? Nope, because once again, the other factor is 1 over x, not x. So that's not going to work. Golly. Maybe inverse trig, right? Function minus number, maybe. Arc secant. Let's see. If that's u squared, then u is 2x. Good. And if that's a squared, a is 3. All right, two things we have to check for. The derivative of that needs to be in the numerator. Is it? No. Darn it. So we're off by a 2. That's not a problem. And whatever we're calling u needs to be conveniently out front. Do we have a 2x out there? No. So here's where it becomes high maintenance. We need to make it look like the form. We can put the correction in our final answer, but we need to force it to look like the form. So here's what we do. I need that to be a 2x out front, so no problem. I'm going to multiply by 2 in the denominator, which is legal so long as I do what? Multiply by 2 in the numerator, which is really just cleverly multiplying by 1. Now let's reevaluate. Do I have a 2x conveniently out front? Yeah, I do. And what's the derivative of 2x? 2. So now you have the option of saying that we're not off by anything and the 2 gets packaged back up, or you could have the 2 going along for the ride and be off by a 2 and have a correction of a half. Either way, what's going to happen? They're both going to be gone. So at that point, it's just a preference. I'm going to go ahead and say we're not off by anything. We'll package the 2 back up. So it's gone. So we just go straight to the rule now. There's no correction. Do we have a 1 over a in front? Yes, we have a 1 over 3 arc secant of the absolute value of u, which is that over 3 plus c. Now again, that might not be the multiple choice answer because it does simplify. We could say that that's the same as 2/3 absolute value of x plus c. Or you could put the entire 2/3 inside. But you could pull out a number from inside the absolute value that's already there as long as you make it positive. Well, 2 is already positive. So those are all the same. Okay, and then we get to this one here. Yeah, now this one, again, quickly going through the motions here, you got e to the 2x. That could be your inside function. It could be a power rule. But what's the derivative of e to the 2x? E to the 2x times 2. Do we have a 2e to the 2x on the top? No. We're off by a 2e to the 2x. Can we make a correction of 1 over a variable? No. So it's not going to be a power rule. So really, is it going to be an arc sine or an arc secant? If you walk up to it without thinking, you might think arc sine because you just see a single radical and you see a difference of two things. But remember, arc sine is number minus function. And subtraction is not commutative. This one is function minus number. But what's missing? In the previous problem, we were missing a 2, but at least we had the variable part there. This one has nothing out front of the radical other than a 1. So it's kind of mysteriously not looking like an arc secant. But we have no other option. So let's just see. Okay? If that is u squared, then u would be what? Keep in mind that e to the 2x is the same as e to the x quantity squared. So u would be what? E to the x. And if a squared is 1, then a is 1. All right. Two things need to happen. The derivative of what we're calling u, e to the x, needs to be in the top. Do we have an e to the x there? No. Diggity darn it. And we can't make a correction of a variable, so that's not good at all. But we also need whatever we're calling u to be out front. Okay. Well, just like before, we can multiply by e to the x out front, which is a variable function, as long as we multiply by the same thing in the numerator. Now that right there is the proverbial 2 birds with 1 stone, right? Because now we have exactly what we need out front, and what's the derivative of e to the x? E to the x, which is now in the numerator. Yay! So now it does fit the arc secant pattern. There's no correction. We go straight to the rule, which is what? Do we have a 1 over a in front? Yeah, but it's just 1, so 1 over 1, it's just arc secant of u over a, the absolute value of u over a, but a is 1, so it's just that. And of course, what do we know about e to the x? It's always positive. So those can become parentheses. Yeah, there you go. Now, I don't know if you remember this, but we had that problem as a derivative problem earlier in the year when we first met the inverse trig functions. And I told you when we worked it in reverse that the e to the x are going to divide out, and we're going to get to a day sometime in the future where they're not going to be there, and you're going to be like, oh, we need them. I wonder where they went. I'm going to be like, remember that they divided out. So if they divided out, we can put them back. Well, guess what? That day has arrived, and that moment has passed. Yeah, it came and went, just like the Pekingese. Okay, any questions on example 16? Arc secant. Doesn't show up a lot, but when it does, kind of fun. High maintenance. Whew, like the diva ladybugs. Yeah. Sometimes I wrote this stuff. Let's see what I was thinking. Sometimes we need to algebraically alter the integrand to resemble something we recognize how to do. And sometimes, like parents of fighting siblings, we need to send each kid to his own room. What the heck does that mean? Now, y'all did this one with Mr. Peck. I know that, right? Y'all did example 17? No. Oh, you did not? Okay. 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 This one was on the board when I came in, so I guess he did it with a fourth period. But, yeah, anyway. Y'all stopped and he told you good stories about Artesia. No? You watched the announcements. Okay, okay. Well, we still got 20 minutes, so let's see. I don't know if that's like a clue or a hint. Like parents of fighting siblings, we need to send each kid to his own room. Okay, so we walk up to the problem, and the first thing you might notice is that it's a quotient of two variable functions. You might immediately gravitate towards what as the inside function, even before you have to like necessarily rewrite it. 4 minus x squared, right? Because if you brought it to the top, it would be to the negative 1/2, so it would be inside the more interesting outer function, and it itself is a higher degree than x plus 2. So let's see. Let's see if it's just going to be a straight up power rule. What's the derivative of 4 minus x squared? Negative 2x. Is that what we have in the numerator? No. Are we only off by a constant? No. Uh-oh. This looks pretty dire. Okay? Notice that if that stupid plus 2 weren't there, to use the subjunctive case, I would only be off by a negative 2, right? And I could have a correction of negative 1/2, bring it to the top, and use the power rule, right? So the plus 2 is causing us problems from using the power rule. But to defend positive 2, but x started it. I was here first. Okay, fine. So let's hear the argument. If x were gone, then the 2 would be the only thing up there, which we could pull out front. And now it would be a what? An arc sine. Okay, it would be an arc sine. So without the 2, it's a power rule with a correction. Without the x, it's an arc sine. All right, you two, quit fighting. You go to your room, and you go to your room. What does that mean? Well, we're going to split up the terms. That's what it means. And this is going to be one of our strategies. Split up terms in the numerator. It's a lot easier than splitting up terms in the denominator. Now, I'm not going to give them each their own integral. You certainly could with their own dx. I'm going to say it's x over 4 minus x squared. And then plus 2, well, let's go ahead and do it like that. 2 over the square root of 4 minus x squared. So as long as every term that you split up in the numerator or a combination of terms gets the entire denominator, it's legal. Okay, we saw something similar to that when we did like the derivation of the derivative of cosine and sine, where you had to split everything up and maybe even take a combination of terms. But as long as they're both over the entire denominator, it's good. So what you've done now is you've created two terms, which means you've created two separate problems, each requiring their own individual analysis. So there's enough math for everybody. There doesn't need to be any fighting. Okay? So in the first one, if you now want to bring that to the top so that you can help yourself with the power rule, that's great. And if on this one, if you want to bring the 2 out front so you can assist yourself with the actual antiderivative, that's great. Okay, so let's go ahead and integrate. I would recommend integrating both terms at the same time. If you integrate one but not the other, Then you have the burden of keeping the integral and the dx on the one that hasn't been done yet, and a plus c on the one that you have done. So let's just integrate it all at one time. All right, this one here, the first term, there's your inside function. You're off by a what? -2, right? So we have a correction of -1/2. The x gets packaged back up. Blob to the -1/2 by the power rule then becomes, leave a little space, -1/2 plus 1 is +1/2. And of course then instead of dividing by 1/2, we'll multiply by its reciprocal 2. So that takes care of the first term. I'm not going to put a plus c yet because it's all part of the same integrand. Now we just mosey over to the next one. Plus 2 goes along for the ride. This is a squared, so a is 2. That's u squared, so u is x. And I would recommend highly identifying, explicitly like that, a and u. Now, what's the derivative of u? What's the derivative of x with respect to x? 1. Are we off by anything? Nope. So we have a rider 2. There's no correction. We have a equals 2. Do we have a 1 over a in front? No, because this one is arc sine, the only one without a 1 over a. So we go straight to the arc sine of u over a, which is x over 2. And now we've integrated both terms, and we finish it off with what? Plus c. C for corporal punishment. If you don't behave, you're going to get spankings. Used to paddle in this school, right? Mr. Peck himself, right? I've shown you his paddles, right? The guy that was here on Tuesday used to paddle everybody on campus. Everybody on campus.
They don't know who Reimer is, do they?
Yeah, they know who Reimer is because he was still here last year. Yeah. Reimer still was the only guy that gave lick. Yeah. So this was Mr. Peck's paddle, and some of my classmates are on here. I am not. Yet you signed the paddle after he got you. Yeah. This is one of many paddles. The other one's on the wall over there with the holes filled in it. Of course, you know why the holes are there. Less air resistance, right? And they tattooed you when they hit you. Crow, Aaron Johnson. God, I still talk to him every once in a while. What did you do that day, Crow? Golly, just behave. Just behave. He was an imposing fella back in the day. Yeah, but you got to sign the paddle. But I'm not on here. I was a really good student. Yeah. Anyway, I was a nerd. No, I was actually just afraid. I was just afraid is what I was. I respected him. Okay. Anyway, plus C. That's the moral of the story. Don't forget plus C. Plus C. C for a constant, really, right? Okay, so what's one of the strategies now that we have? Split it up. Split it up. Every term over the entire denominator or any combination of terms. What did you get licks from Reimer for, Mr. Cook?
You know Ms. Zeiss?
We know who Ms. Zeiss is.
So it was after one of the tax tests. We passed 30-minute class, and there was her, and I glued pretzels to her mouth.
To her mouth?
No.
Oh, her mouth. I was like, if you glued them to her mouth, then she was complicit with that.
And so she thought she was funny, so she went to my football coach, Walker.
Coach Walker.
And I thought I was going to have to run or something like that. And he said, well, you're going to have to go get a lick from Reimer. So I waited a week, and he never called me in there.
Oh, yeah?
Coach came up with like, well, why haven't you got your lick from Reimer yet? I said, well, he didn't call me in, Coach. He goes, no, you just go ask him for one.
Yeah, because he kind of did it. He'd call home first to make sure it was okay. But of course, your dad was like, yeah, hit him twice. Right? Yeah. But yeah, we don't do that anymore. But it was pretty much a common thing. For every little infraction, you'd go out in the hall. And Mr. Peck was the guy who did it. So if you were in another person's class and you did something wrong, they would come get Mr. Peck and he would paddle you. And it would be in the hallway. He was down there in the 200s now, and it was before they had the acoustic ceilings like this. So it was kind of like just like a big old echo chamber, and he'd hit it and be like, whoosh, 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 all through the school, and everybody would be like, whoa, someone just got a lick. Yeah. So anyway, it's good stuff. Well, no, it wasn't like public hangings or anything. No. Okay. Example 18. We have three integrals here, a, b, and c. Two of them we can currently do, and one of them we cannot. Okay? And we need to understand which ones we can do and how to do them, and why the one we cannot do is not readily available to us at this moment. So notice that they all have very similar denominators, root 5 minus x to the fourth. Yeah? But the numerators are what's different. We have a 3x on the right, a 3x squared, and a 3x cubed. Okay? Let's just take them from left to right. Okay, the first one here. Your mental flow chart. Again, you should just quickly mentally look at the radicand and say, maybe it's a power rule, maybe that's the inside function, maybe I'll have to bring it to the top, and maybe I'm only off by a constant. What's the derivative of 5 minus x to the fourth? Negative 4x cubed. You compare it to the other factor, and you're like, I got it. I got the x cubed, so I'm going to be able to do this one. So the 3 is going to come out front. Now you're going to rewrite it. You got x cubed, 5 minus x to the fourth, to the what power? Negative 1/2. Now maybe you can go right to the answer without doing that, but I would caution against it because it's easy to make a careless mistake. So now that you have it in that ready format for the power rule, the 3 goes along for the ride. You're going to have a correction of what? Negative 1/4, right? Negative 1/4. And then the x cubed gets packaged back up. And then step 2, the rule of integration is the power rule. Blob to the negative 1/2 becomes blob to the positive 1/2 with a what out front? 2. Plus c, drop the blob right in, and you're done. And then you combine your writer with your correction with your rule constant to get whatever the answer is. Negative 3/2 square root 5 minus x to the fourth plus c. Perfect. Nothing to it. Okay, the next one. We have 1 less x in the numerator. 1 fewer x, I should say. The derivative of that is 4x cubed. Huh. Are we off by just a constant? No, we're missing an x. And when you're off by an x, you can't just go to the power rule. So that's not good. So if it's not going to be a power rule like the one on here in part A, maybe, right? We got a radical in the denominator. It's number minus function. Maybe it's arc what? Maybe it's arc sine. Let's see if it's arc sine. If that's a squared, then a is square root of 5. If that's u squared, then u is x squared. Let's see. What's the derivative now of x squared? 2x. Ah! We're off by an x again, but now on the other side. Can we make a correction if we're off by a variable? No. So do we know how to do this one? No. We overshot the numerator's degree and we undershot it, so right now we can't do. So can't do parentheses yet. Dot, dot, dot. I'm coming back for you, though. Okay, all right. We're going to learn some advanced integration techniques later on. And maybe we'll return to that one and see if we can dominate it.
Pardon the interruption, teachers. Please turn your TV on to channel 4 for these morning announcements. You may also watch them at mbhstv.com. Thank you.
Okay, so part C now is pretty much a foregone conclusion in light of our analysis from part B, right? We know that the derivative of that is 4x cubed. We're off by an x squared in the top. We tried an arc sine. A was the square root of 5. U is x squared. Oops, x squared. The derivative of x squared is 2x. So now we can do it. We're off by a 2. So 3 goes along for the ride. We have our correction of 1/2. It's arc sine. Does it have a 1 over a in front? No. So it goes straight to arc sine of u over a. And, of course, we finish it off with a little corporal punishment. Only if you leave the plus c off. That would be a paddleable offense. Okay? Paddleable. The ability to be paddled. Okay. We got time. Let's do it. We're BC. We got to keep moving, right? Because there's only what until the AP exam? 90 days. That's right. It's time to develop some more strategies of what to do when the integrand is unrecognizable. We already have a couple of strategies, right? Like splitting up the terms, trig identities, praying. What else? Guess and check and revise and check again and keep revising. Just never, ever, ever surrender, right? Ever give up. Find each of the following, if possible. Oh, is that to deter me? Is that a challenge? If possible. All right, here we go. We got 3 over blob. I know that I'm going to gravitate immediately in my mental flow chart to the denominator. Maybe it's a natural log rule. Perhaps, maybe. That's a big maybe, right? Because if this would be my inside function, I would need its derivative to be in the numerator or only off by a constant. What's the derivative of x squared plus 6x plus 9? 2x plus 6. Do we have a 2x plus 6 in the top? No. But notice I could factor a 2 out. Do I have an x plus 3 in the top? Or a multiple of x plus 3 in the top? I could be off by a multiple. I don't even have an x in the top. Darn it. So it's not going to be a natural log rule. Sorry, tried. Maybe it's going to be inverse trig, huh? Inverse trig? There's no radical, so maybe arctangent, right? Is this number plus function? Or function plus number? No, it's function plus number. What the? Okay. So, man, if you find yourself now at the very end of your rope and you've gone through everything and you're barely hanging on, you know what you say? F it. F it. Which doesn't mean let go, right? It means factor it. Let's try to factor it. Factoring is, man, y'all came in perfectly on cue like y'all heard that before. Factoring is a good thing. Does this one factor either into a binomial squared or a product of two binomials? Absolutely, it's x plus 3 quantity squared. Now that we factored it, show up, come on, there you go. We reevaluate it. It's like a brand new problem. We've already got the 3 out front, so we gravitate. There's our inside function. What's the derivative of x plus 3? 1. Do we have a 1 in the top? Yeah, we do. Are we off by anything? Nope. Now, because I know I have to use the power rule, I take that extra step of rewriting it in the numerator. Only if it's in the denominator to the first power is it going to be a natural log. Otherwise, I would recommend rewriting it. It's easy to make a mistake. So here we go. We're not off by anything, but it's a power rule. So blob to the negative second becomes blob to the negative first. And then we divide by negative 1, which is the same as multiplying by negative 1 plus c. And then we simplify it negative 3 over x plus 3 plus c, and we are Brooks and done. Yeah. Okay. Fun, right? Factoring. Let's try another one. Letter B. Hey, that looks a lot like letter A. The only difference is what? Yeah, the numbers. Instead of plus 9, it's plus 10. We got one more joining us. Hey, the more the merrier. The more the merrier. But you know what? The derivative of that is not going to be the numerator. Does that one factor anymore? Factors of 10 that add up to 6? 5 and 2, 7, no. 10 and 1, no. Quadratic formula to find the roots. Yeah. Does this one even factor into two binomials or a binomial squared? I don't think so. So, oh my gosh. You know what? Here's what. I'm going to pull the 3 out. It was factorable when that thing was a 9, wasn't it? Remember problem A? I'm going to call that x squared plus 6x plus 9 plus 1. No one invited you. Ah, yes, that's where we're going with this. Very good. We only have the insight to do that because we did problem A first. We're going to do it that way with the insight, and then we're going to say what to do if we don't have the insight of problem A first, and Berquist already gave it away. Which is great, yes. That's going to factor into x plus 3 squared plus 1. Now it fits a what rule? You have a function plus a number with no radical. That's an arc, not arc sine because it doesn't have a radical. It's arc tangent. This whole quantity is u squared, so u would be x plus 3. And that plus a number, that's a squared, so a is 1. Now, what's the derivative of x plus 3? 1. Are we off by anything? No. So 3 goes along for the ride. Do we have a 1 over a in front for arctangent? Yes, but when a is 1, you don't need to write it. But maybe for inventory purposes, so you know you didn't forget it, feel free to write it. No correction, so it's just arctangent of u over a, which is x plus 3 all over 1, again for inventory purposes, plus c. And of course, you can simplify that, make it a little prettier, x plus 3 plus c. Now, yes, what to do if we hadn't done a first and known that 9 was going to make it factorable? One of our strategies is going to be to complete the square, and I will show you how to do that tomorrow. okay, in case you have forgotten. So we'll pick up with doing example 19B again, but we'll do it a different way. We will finish the notes tomorrow because I'm going to push. Tomorrow's Friday, so it looks like we get to cozy up with the worksheet over the weekend, all right? This is probably one of the most important sections we'll be doing all year long.